Hello guys, this is Daniel Pinheiro from danielpm1982.com and welcome to one more video about Docker. And as I always say, this video is a continuation of other lectures. So if you haven't watched the last lectures, you should go back and see them, because everything that we're gonna see this video and on is a sequence since the first lecture of this course. So as you may remember, last lecture what we've seen was how we can run, for example, a container containing some DBMS and some databases we want to use in our applications. And separately from that, how we can run another Docker container containing our application and springboot application, for example, and linking that the container with this springboot application to the other container containing the DBMS and the database we wanna use at the springboot application. So what we did last lecture was to create two containers, one containing the DBMS, the MySQL database, with a specific database we created, as well as with a username and password for accessing it, both from inside the same container as from outside, for example, from our Spring Boot application. And we also created a container for our Spring Boot application, configuring the application for accessing the MySQL database by setting some configurations at the application.properties file inside the Spring Boot application. And then we Dockerized and published it to dockerhub. And also later we tested clearing all Docker objects used locally and running again both containers directly from dockerhub. The container we created for containing the specific database for our application and with the username and password inside, we created from the MySQL image, official image, by running it with this command line here, sudo docker run, then the name parameter here with the name of the container we are creating now locally, named meeting app MySQL container, then with the -p, which is the publish parameter. It's not actually the port. We do have the port command inside Docker CLI, but this -p here is not from port, it's from publish. So we could even use not -p. Instead of -p, we could actually use --publish. And as we've seen, this flag or this parameter here works by publishing an internal port from inside the container we are using and mapping that to an external port from our operating system, in this case 3306 and 33060. Then we have the -v parameter through which we map the internal volume of the container we are creating from this official image to an external folder at our operating system, in this case /home/daniel/temp/mysql-data. And through that we not only map from the internal volume to outside, but in case we delete the container, we also can map in the opposite way so that we can restore or make use of all saved data from outside the container back into the new created container. So we also have seen that a lot. Later we have a single environmental variable here, which is MySQL root password, that we set as root. And for creating the container from the official MySQL image, this is the only demanded environmental variable that you have to pass. We at least have to pass the user password here so that we can run it at least as the root user. And then what we also have done is to, after creating the container, get into the container using the docker exec command. And when inside this MySQL container we just created using the exec command, we then created manually through the MySQL CLI a specific or custom database. And in this database we have not actually created the tables manually. We let that for the Hibernate to create when running the application linked to that MySQL container. But we did create the custom database at least, and then we also created custom usernames and passwords for accessing that database without using the root and using an actual username and password with its own privileges. So after we had that MySQL container running with the specific database, username and password, we then linked that database container with our application container, which we created using this line of code here: sudo docker run, the name of the application container, app springboot container, and the new thing that we saw last lecture was the link parameter here, which basically defines a connection between the current container, which in theory is isolated from any other container. So by default, all Docker containers are isolated within themselves. So from one container, if they are not linked somehow, and we see some details of it in this lecture, but if they are not linked at all, it's impossible for one container to access the other container. So for allowing that, for example, here for the app springboot container to access the MySQL container, we had to link them by running the second container, which is actually the recipient container, to the source container. We have two containers. One is the source, which has our database running, and we have another container which is the recipient container that may now access the source container here through this link. And here, as values for the parameter link, we have the name of the container that you're linking this recipient container to. So here is the name of the source container that must be already running so that this other container can connect to it. So this is the first container, the source container that should be running already when we call these running commands on the second one. And here is the alias for the link connection between those two containers. So here is the name of the source container. Here is the alias to the link from this recipient container to the source container. So if I not have said that last lecture, this MySQL here can be any name you want. It doesn't have to be MySQL because it simply is an alias for the link connection between this source container and this recipient container that will be linked through this connection here to this source container. So this is the name of the connection. And here, as we already know, we are exposing the 8080 port from the Spring Boot container so that external applications, for example, our browser, can access the application inside this container. Because it's a web application, so we gotta have access through the browser to it. And by default, the port will be 8080. And also we pass as an environmental variable here the host name used at the application.properties, which will connect from inside the application to the database. And as we've seen, we cannot use, when using containers, we cannot use the local host, so we gotta use as host name the name of the container we're linking to. So the name of the container that we're linking the application to is the meeting app MySQL container. So you gotta use that as the host name at the application.properties in order to the application to be able to access the database in the other container. And here also, as we know, we are using here the detached mode -g for the container of the Springboot application. And here the name and version of the container already published at dockerhub at my dockerhub profile. So, and actually you could only call this directly from the Docker image. This is the image of the application at my Docker account. If you had the image already downloaded locally. If not, if you're calling it directly from dockerhub, you gotta also pass the namespace of the Docker account at dockerhub. So the namespace of my account is DanielPM1982, and then you can use the slash and the name of the image along with its tag. So this is what we did last lecture. And now what I wanna teach you is a little bit more specifically about links, but it actually is impossible for me to explain links in full or in a minimal way so that you can understand it without explaining Docker networks. So you see that links is inside the networks architecture of Docker, so I can't actually explain how links work without first explaining how Docker networks actually work. At least one kind of Docker networks, which is the bridge network that we're gonna see in this video. So I'll have to make a pause on the manipulation of the applications we are Dockerizing and testing so that I can explain a little bit theory about Docker networks. Then I'll explain how links actually work. We have not seen even the smallest part of it. So I'll first have to explain networks, then links, and later we'll go back to these two containers that we've seen and that we have tested in parts already, so that I can tell you how to use links in a more elegant way. For example, parameterizing better and refactoring both the running of the MySQL container as the running of the Spring Boot application container. And in case you haven't realized yet, this course is heavily based on practice, and of course I haven't had the time to enter much in Docker theory. For example, we have not yet seen much of the Docker documentation because it would extend the length of this course too much, and I decided to follow a more practice approach. So we have not yet discussed theory about Docker or about operating system so far that much, but now I have to make an exception so that we can actually understand how networks work, so that we can then learn how links work, and later what are the alternatives that we can use from Docker architecture or from Docker API instead of using links. Why? Because as we're gonna see in this video, I have not yet told you that, but links is actually a deprecated syntax from Docker since networks were created. So instead of using links with a certain type of network, and we're going to see which type of network is that, you should not use links, but use these alternatives we have at Docker. For example, volumes with configuration files, or Docker Compose that we're going to see at the end of this course, and not actually use links. But I had to tell you the whole evolution of Docker, so I kind of followed a bottom-up approach so that we are learning the most basic and lower way of working with Docker, and then we will learn easier ways of doing the same thing but using high-level API from Docker, so that, for example, Docker Compose, which is much easier to use than calling all these running commands individually and dealing with all these environmental variables. So first, in this video, we'll have to learn a little bit about the theory of networks. Then we'll study what that has to do with the links that we already have seen, and how we can call the running commands that we have used last lecture in a more elegant way, in a more parameterized and reusable way, for example. And then I'll tell you how to, instead of using links, how you can simply use Docker Compose and do the same thing. One more thing that I'd like to advance to you in this lecture, as we are stopping to discuss a little bit of theory, is that we have discussed a lot of Docker objects. For example, we have discussed about images, we have discussed about containers, we have discussed a little bit about volumes. And for example, regarding volumes, there are a lot of other approaches you can choose. So we have shown you one way of working with volumes, but there are a lot of other ways you might have to work in different scenarios. We are using volumes here as the easiest way, but for example, you can create specific volumes, configure them, and use differently from what we have used so far. So far we have simply used the -v in a local path for mapping internal volumes from inside the container to outside in a single local same machine. But of course you can use remote volumes and all of that. So if you want to know more about volumes, you can simply go to the documentation also. We're doing that for networks, but if you want to learn more also about volumes, you can read about volumes at the documentation, because there are other things that we have not yet mentioned about volumes. Another objects that we are not using here are swarm nodes and swarm services. Actually, we are not talking about Docker Swarm anyway in this course, because it's a more advanced level. But shortly, what Swarm actually is and what Kubernetes also are platforms to manage your Docker containers. So the containers we're using in these examples are standalone containers, and we are basically linking them either through the links or through networks, but we are not actually using platforms to manage those containers. So we are not using Swarm, and we are not using Kubernetes to manage those two containers. We are managing them directly or manually. But if you want to learn about Kubernetes, which were created by Google and is an open source platform, very famous, for example, in cloud if you want to publish your containers in cloud, and especially if you want to create clusters of containers in cloud, you'll probably be using Kubernetes. If you want to read about that, you can go to the documentation as well. And Swarm is similarly to Kubernetes. It's also a native platform from Docker. It was created from Docker while Kubernetes were created by Google. The applications we're using here are pretty simple, so we shouldn't be using any orchestration. That's how these platforms are called. These are platforms for orchestrating containers, Docker containers. So they're called Docker Container Orchestrators, both the Kubernetes as the Docker native swarms or swarm services and nodes that you can create for managing, for automating the management of the creation and the destruction of containers, for failure tolerance, for load balance, for managing availability of your applications, and so on. And one of the main objects of Docker, of the Docker ecosystem, are Docker networks. So enough talking, let's go to the Docker documentation and start learning what these Docker objects called networks actually are inside the Docker architecture. So let's start with a brief overview about networking. As you all may know, networks are a way that operating systems of any connectable machine has that allows one machine to connect to another machine despite the operating system running in those. So one machine running Linux may connect using networks to another machine running Windows, as well as that can connect to another machine running iOS and so on. So you can really create a cluster of machines running different operating systems that may connect one to another through an agnostic way called networks that globally constitutes the internet that we all know. So in the case of Docker containers also, Docker technology is actually a pretty much an extension of operating systems, so and especially Linux system, because it's all based on Linux, despite the Docker service is running on a Linux and or at an iOS or at a Windows machine. The thing is that Docker service in each Docker container kind of extends what an operating system is. So inside each container you may have an isolated operating system. It's not actually a virtual machine with a whole operating system inside it, but it is an extension of the operating system of the host operating system that you have in your machine, on which you're running the Docker engine or the Docker daemon servers, so that every container created from one or different images, Docker images, they also extend that host operating system, and everything that applies to an operating system also applies to what's running inside a Docker container, so including networks. So the same way you can link one operating system in one machine to another operating system on another machine, and despite those operating systems are the same type or different types, you can link and make different softwares or different systems connect through the TCP/IP network using network management systems, which in the case of Docker is the Docker service itself. So in a way that if you want to isolate, in this case the containers, you can, and if you want to configure what to share between different containers or what containers to link in a default or in a user-defined custom network, you also can controlling not only the connection, but including the security and safety of the data shared between those two containers, Docker containers, or if compared to operating systems, the data shared between two different machines. So having that in mind, we are not actually entering details about how networks are implemented, either in operating systems or in Docker. And actually the documentation of Docker also lets it clear that it doesn't enter in details about implementation, about, for example, IP tables in Linux, where the routing of IPs and the filtering of those IPs are managed, or in the case of Linux, how the routing rules also are set, because it's a kernel level knowledge about how operating systems are implemented, either in Linux or in Windows or in iOS. And we also won't enter in details about how internet or networks are implemented in Docker or in Docker containers. But what we want to share with you is, for example, what are the types of networks that specifically are available for Docker users to choose to use in different contexts, including in our examples that we have implemented and tested so far. And all the theory that we're going to see in this course is taken from the Docker docs. So you can go to docs.docker.com and to 4 parts of that documentation. You can pause the video and see here the link for each of those 4 parts. 1, 2, 3, and 4. That's the 4 sections that I want to discuss with you, so that we can understand about networks and later about links, and then apply what we've learned into using best practice for running the containers we've run in a better way. So here it's the beginning of how networks are leveraged into Docker technology. It talks about how platform agnostic the implementation is when working with Docker, for example. As we've just mentioned, you may have Docker running different platforms on different computers in cloud and whatever, and the applications running inside each container run by those Docker services in different computers or in cloud, for example, may communicate between them without even knowing in which system or in which operating system they're running, just by knowing the IP or the container name linked to that IP, for example, when run using Docker services. So it also talks about the scope of the topic, that it won't enter in details about implementation. And here what I want to share with you are all the types of networks or network drivers that we have inside Docker architecture. And you may choose any of these drivers and easily set them using Docker CLI, depending on the context in which you want to use your Dockerized applications. So Docker's networking subsystem is pluggable using drivers, so it's easy to connect and disconnect, to use or to change the drivers you're using, depending on the context. If you change the context, you just change the driver. Several drivers exist by default and provide core networking functionality. So these are the default drivers, network drivers that come with Docker by default. But you can also, as here below, you can also install and use third-party network plugins with Docker, or custom network drivers for custom networks. Depending on very specific contexts, you may have your own network that you want to configure and somehow set in a different way from the other available ones. And these plugins are available from dockerhub or from third-party vendors. See the vendor's documentation for installing and using the given network plugin. But what I want to share with you are the types that already come with Docker, especially the bridge network driver or the bridge network type, because this is the type of network that we're gonna use the rest of the course, the bridge. Okay, so the bridge Docker network is the default network driver. So if you don't specify a driver, as we are not specifying, so always connect to what we've been doing so far. We have not yet specified any specific driver, so the network driver we've been using all this time without knowing is the bridge one, because it's the default network driver. So if you don't specify a driver, this is the type of network you're creating and connecting to each of your containers. So every time we ran a container from any of the images we've used so far, we simply used that container connected to a bridge network, because that's the default one. And as we didn't specify any other specific network, the bridge network has been the one we've been using so far without even knowing. So it's kind of the automation Docker does, so that each container has at least one network. As it says here, it's very easy to change that network to other ones. We'll learn how to create networks and plug and unplug different networks in a moment. So bridge networks are usually used when your applications run in standalone containers, and that's what we've also been using so far. Standalone containers that need to communicate. So we've been working with two standalone containers, the BMS container or MySQL container, and another container, the springboot application container, and we want those to communicate. So the ideal network to use in this case is the bridge network that we've been working so far without even noticing, but that from now on we'll change a little bit and set specifically the subtype of bridge network that we're going to use. We'll see in the next part of the documentation the types of bridge networks that exist. We've been using one of the bridge network subtype, and then we'll start using the other type or subtype of bridge network, and I'll tell you why in a moment. But just showing the other ones, we have also, other than the bridge network, we have the host network, also for standalone containers, but through which you can remove the network isolation between the container and the Docker host, which is also the default in the implementation of Docker. There's an isolation between each container and the Docker host itself. Also, obviously, an isolation from the container and the operating system in which the Docker host runs. And the host type takes away that isolation between the container and the Docker host and uses the host's networking directly. If you want to see more about it, you can just click here and it will go to the parts of the documentation about host networks. We also have the overlay network driver, which connects multiple Docker daemons. In our case, we are using only one Docker daemon, so if you want to use multiple Docker daemons, you'll probably be using, instead of the bridge network or bridge network subtypes, you'll be using the overlay network. So this network connects multiple Docker daemon services all together and enable swarm services in case you're working, for example, with clusters of containers in each of those swarm services and nodes to communicate with each other. So if you're using Swarm, or if you're using Kubernetes, maybe you'll be using overlay networks instead of the bridge networks. So you can also use overlay networks to facilitate communication between a Swarm service and a standalone container, or between two standalone containers on different Docker daemons. This strategy removes the need to do OS level routing between these containers. So the application of overlay networks are if you wanna remove the OS level routing between your containers and you wanna use different Docker daemon services, or if you're using Swarm services instead of standalone containers, or a combination of those. In our case, just have in mind that we are working in our examples with standalone containers and not with Swarm services or Swarm nodes, different machines, for example. And also, we are not working with multiple Docker daemons, which is the other possible application when using overlay networks. So we are working with standalone containers and with a single Docker daemon managing those standalone containers. So in this case, in our case, the bridge network is the best one, but have in mind you also have the host and you also have the overlay network drivers that you can easily set, and they are kind of pre-configured by default by Docker, so you won't have any work in implementing them because they are already pre-implemented by the Docker development team. So these are basically network drivers that you can simply use, and they come out of the box from the Docker implemented architecture. So we also have the IP VLAN networks, which give users total control over both IPv4 and IPv6 addressing. If you wanna manually work with IPv4 and 6 addressing, you probably use IP VLAN network drivers. So the VLAN driver builds on top of that in giving operators complete control of layer 2 VLAN tagging and even IP VLAN at 3 routing for users interested in underlay network integration. So if you are a network integrator, you probably make use of IP VLAN, which obviously here is not our case. So, and we also have the MAC VLAN. MAC VLAN networks allow you to assign a MAC address to a container, making it appear as a physical device on your network. So if you want to work with IoT, for example, you probably be using MAC VLAN, or if you want to simulate IoT hardwares but using software, probably you'll be using MAC VLAN for assigning MAC addresses to each container and simulating software-based physical devices in your network. So the Docker daemon routes traffic to containers by their MAC addresses instead of through the IPs from a normal network like the bridge. Using the MAC VLAN driver is sometimes the best choice when dealing with legacy applications that expect to be directly connected to physical networks rather than routing through the Docker host's network stack. So if you want to learn more about this type of network, just also click here on the link on the right. The documentation of Docker is actually pretty simple to be used, although a little bit extent, and also you have here the guides, which is what we are using, but also you have the menus about each component of the Docker architecture and the technologies themselves, the applicated part of it. And also you have the reference here and the samples part. So if we go to the docs.docker.com, we can select here the parts of the documentation. In our case, we are seeing the guides, and specifically about configuring networking, which is inside Run Your App in Production. If you see here, you also have the documentation about how to deploy your app on the cloud, how to set up your CI/CD for continuous integration, continuous deployment, how to develop with Docker, and some other resources here. But continuing our discussion about the network drivers, the other last type of network drivers in the Docker architecture is actually no drive at all. So it's the none type. And for the containers using this type of driver, you're telling the Docker daemon to disable all networking. So it's usually used in conjunction with a custom network driver when I use any other than these other drivers. Because as we've already mentioned, if you simply do not specify any driver, it will set by default the bridge driver. So if you do not want any of these drivers to be used, you gotta use the none type of the driver and eventually specify any custom other driver telling the Docker daemon not to use any of these default network drivers that come with Docker. So that's it about network drivers when running your application inside Docker containers. And just remember that throughout this course, we'll be using only the bridge network. Why? Because we're using throughout this course standalone containers, and also we're using one single Docker daemon or one single Docker engine, as well as all of them in one same machine. So the best driver in this case is the bridge driver. But as we're going to see, we have basically two types of bridge drivers that we're going to see in the next part of this documentation. So the other part is this one. Just may pause the video and get here the URL for it. It's also inside the same part of the Docker documentation, inside guides, inside Run Your App in Production, inside Configure Network, but now use bridge networks. So everything we're going to see in this part of the documentation is only about the bridge networks, which is the network we're using in our practice. So what is a bridge network? In terms of networking, a bridge network is a link layer device which forwards traffic between network segments. So a bridge can be a hardware device or a software device running within a host machine kernel. In our case, the bridge is a link between two containers. So here it says, in terms of Docker, a bridge network uses a software bridge, not a hardware device. It's a software bridge which allows containers connected to the same bridge network to communicate between them, while providing isolation from containers which are not connected to that bridge network. So what does a bridge network do in terms of Docker containers? The bridge connects all the containers set at that bridge, at that specific bridge, so that each container or each application running inside each container may communicate between them, may communicate one application with another application in different containers in that same network without even knowing any other specific low-level detail or even knowing that they are in different containers, let alone that they are in different containers linked by a bridge network. So the Docker bridge driver automatically installs rules in the host machine so that the containers on different bridge networks cannot communicate directly with each other. So for the containers that are linked to that networks, they communicate, but they are by default isolated to any other containers running eventually at that same daemon service, but not linked to that same network. So the bridge network basically has two functions. One is to link any number of containers that you set to run in that same network, and the other function is actually the opposite, to isolate all those containers that are linked through that bridge network from any other containers linked to other bridges or to other kind of networks, but not to that first bridge network. So the bridge links containers to a specific bridge network and also isolates them from other networks if not linked to that same bridge as well. So bridge networks apply to containers running on the same Docker daemon host. That's our case here, as we've mentioned. And for communication among containers running on different Docker daemon hosts, you can either manage routing at the OS level, or you can use overlay network, as we've previously also said. So when you start a Docker, a default network, also called bridge, and this here is pretty important for our practice. So have in mind that when you start a Docker daemon service, a default bridge network, also called, it has actually the name bridge. It's a bridge network type, and its name, the name of the network, if you inspect, and we'll do that later, the name also is bridge. So every time you start a daemon service or a Docker engine, a default bridge network is created automatically, despite any images or containers you might have or not. You actually may have no containers at all, but you'll have the default bridge network already created at the start of the Docker engine, and newly started containers connect to this default bridge automatically unless otherwise specified. So unless we specify a different network, or unless you specify a user-defined network, bridge network, that's what we're going to see in a moment, that container will be linked automatically to a default bridge network. It's not only a bridge network, it's a subtype of the bridge network called default. So you have one and only default bridge network, and you also can create any other number of user-specific bridge networks, which we're going to see in a few moments. But if you do not specify that, or if you do not specify any of those other network types or drivers, every single container that you start in a same Docker daemon service will be linked by default to that default bridge network created as the Docker service is initiated. You can also create user-defined custom bridge networks, and this is the best practice that we start to use as soon as we see how to create them, and we will not be working with default bridge networks anymore, as we've been doing so far, as it's actually not the best practice. The best practice is to use user-defined custom bridge networks and not the default one. So user-defined bridge networks are superior to the default bridge networks in many aspects. And what I want to show you now is what superior aspects are these. So for these two subtypes of the bridge network, which is the default bridge network and the user-defined bridge network, what are the differences? And you gotta pay attention to all of these differences because we're gonna use this in our practices throughout the rest of this course. So the first main difference between a default and a user-defined bridge network is that user-defined bridges provide automatic DNS resolution between containers. So containers on the default bridge, which is the subtype of bridge network created automatically when the daemon service is created. If you do not specify any other bridge for your container to be set with, it will be set with a default bridge network, and these containers can only access each other by IP addresses. We'll test that. For the containers we've created so far, for example, we could communicate. For example, we could get into one of those containers using the exec command and ping the other container, not through the other container name, because we have no DNS resolution in default bridge networks, but we could do that through the IP addresses. So we could get into a first container, for example, and ping the other container through its IP address, through the IP address of this other container, because both would be in one same bridge, which is the default bridge network. So the default bridge network is a bridge network, so it allows the communication between all the containers linked to it, but specifically the subtype default bridge network does not allow the DNS resolution of the name of the container in respect to its IP address. So you gotta set manually the IP address if you wanna communicate from one container, from inside one container to the other container with a different IP. You cannot just communicate using the name of the other container. You gotta inspect the IP of the other container and then use that IP in the first container. Unless, and here is one of the advantages of the link flag that we've been using so far, unless you use the link option. So the default bridge network does not allow DNS resolution unless you use the link option, which is considered legacy. And we'll see, starting from this part here of the documentation, why it is considered legacy or deprecated. You can actually use it as we've been using so far, but eventually it may stop being supported by the Docker API. So the default bridge network, if you do not use the link option, it does not allow the DNS resolution between the name of the container and its IP. On the other way, on a user-defined bridge network, containers can be resolved by their name or alias. That's why if you're using user-defined bridges, you not even have to use the link option, because they by default have DNS resolution, and if you refer from one to another through its name, the name will be resolved by the Docker daemon into its correct IP. So either you're using the default bridge network or the user-defined bridge network, they both are bridge networks, of course, and you'll be able to communicate from one container to another, but one of the differences is exactly this, the DNS resolution between containers running on those bridge networks. Just remember that when using default bridge networks, you gotta use the link parameter or the link flag if you wanna use DNS resolution regarding the name of the container and the respective IP. And if you're not using default bridge networks, if you're using, on the other hand, user-defined bridge networks, you don't have to do that, because by default, you have that by default implemented in this subtype of bridge network. So at first, we only had default bridge network, so that's why the link option was created, because we didn't have at the time the user-defined bridge networks. But since the user-defined bridge networks became available, the link parameter or the link flag kind of lost its utility. Why? Because at user-defined bridge networks, the DNS resolution, for example, is implemented by default without the need of the link flag. But this is only one of the differences, but still regarding it, here we have imagine an application with a web front and a database backend. If you call your containers web and DB, here it's exemplifying a situation. The web container can connect to the DB container at the DB, no matter which Docker host the application stack is running on. So in case you use a user-defined bridge network and not the default bridge network, you can simply refer from one container to another. For example, from a container called web, and from inside it, you may call the other container called DB simply by using their container name, in this case web and DB, and not worry about find out their IP, because through that name the IPs will be resolved automatically, no matter which Docker host or operating system you have running in your machine. So if you run the same application stack on the default bridge network instead, you will need to manually create links between the containers using the legacy link flag, and that's exactly what we did in our examples. We created a web container with the springboot application container, and we created another container, the DB container, and for linking them two from the application container to the database container, as we were using the default bridge network, because we didn't specify any other network type, so by default it sets the default bridge network, we had also to use the link flag so that we didn't have to worry about the IPs when connecting from one to another. We simply used at the link parameter, for example, the name of the source container for referring to it from the recipient container, which was, in our case, the web application container. So these links need to be created in both directions. In our case, we created only having as source the DB container, and as a recipient container the springboot application container. But we could also, if we wanted to refer the other way, we would have to create two links, one link at the running of one container and another link at the running of the other container. In our case specifically, we only had to create it on one of the runnings because we only had a communication from the application to the database container. But it actually and obviously adds a lot of complexity to our software architecture, especially if you need to run many containers at once when starting your system. And also, other way that you may manage that is to manually manipulate the /etc/host, which is a text file within each of those containers that basically specify the link between each of those containers and other containers. And you either can manipulate the file manually or through the link flag that will in turn manipulate those files automatically. We'll see that in a moment. When we implement that, we'll be implementing both a simple default bridge network and link two simple containers that are not the ones we've been working so far. They are simpler containers, but we'll be implementing them both using a default bridge network and using as well a user-defined bridge network for you to have a better practice notion or view about the differences between using either one or another. So this is the first difference between those two subtypes of bridge network. The second difference is that user-defined bridges provide better isolation. And why is that? We kind of already mentioned the reason for that. All containers without a network, a dash network flag or parameter specified, if you do not specify which network specifically you want to connect, these containers, when set to run, they are attached to the default bridge network by default. And what's the problem here? The problem is that this can be a risk, as unrelated stacks, services, and containers are then able to communicate. All of them will be set to the same exactly bridge network here, which is the default one. So if you run 20 unrelated containers without specifying any user-defined network for each use case you have for each of those containers, all of those containers will be linked to the same network, and that means that they will all be connected between each other. So from one of any of the applications inside one container, you'll be able to access any of the other containers or applications or data, including database data, running on that same default bridge network. That's one of the main reasons that it's not advisable to use default bridge networks, because that increases the risk that an application that should not have access, for example, to a certain database, because that database is running in a container linked to the same default bridge network as the other application or application container, the other application would be able to access that database intentionally or not. So it increases the risk of security issues, and it turns available a way for actions to occur where there should be actually an isolation between those services running in each set of containers. If, for example, for 20 containers running, you should only, for a specific context, have 3 of those containers having access to one another. You should create a user-defined bridge network and connect only those 3 instead of the 20 to one same default bridge network. So using a user-defined network provides a scoped network in which only containers attached to that network are able to communicate. This is the best practice and the best case scenario for the types of containers we're working, for example, in our practices. So this is the second difference. Now the third difference relates to the plug and unplug of that network to each container. So containers can be attached and detached from user-defined networks on the fly, while when using default networks you can't. So during a container's lifetime, you can connect or disconnect the container from user-defined networks on the fly. We'll test that when we test the implementations of both types of bridge networks. So when using default networks, you need to stop the container if you change the containers that are linked to that default network, or for example, if you reset a container to not be linked to that default network, or on the other way, if you set a container to be attached to that default network, you gotta stop the container and recreate it with the different network options. So to remove a container from a default bridge network, you need to stop the container and recreate it with different network options. So you cannot change as you run a container, as we were running, for example. If you do run a container that connects to the default bridge, you cannot change it or change any configuration of that bridge network related to that container if you do not stop and recreate the container with the different network options. So on the other hand, if you're working with user-defined networks, you'll see that you can actually create many user-defined networks and connect and disconnect any of the containers while the container is still running. So you can connect and disconnect that container to any number of user-defined networks, but not when using default bridge networks. So this is the third difference when using user-defined bridge networks. The fourth difference is that each user-defined network creates a configurable bridge. So if your containers are using the default bridge network, you can configure that bridge network, but that is a single network, and therefore all the containers will be using the same settings if connected to it, such as the MTU and the IP tables rules, and all the routing and so on, and filtering and firewall and as such. In addition, configuring the default bridge network happens outside of Docker itself and requires a restart of the Docker daemon service. So not only all the containers linked or running on a default bridge network, they will share the same configuration rules, and you can change that and specify different rules for each of those containers, but also any change to the default bridge networks that you do, it will require that you restart the Docker daemon service, and of course all the containers running will have to be stopped and rerun after the restart of the single Docker daemon running them. So user-defined bridge networks are created and configured using Docker network create. We'll see this a lot when we exemplify the implementation of both types of bridge networks. So you see, it's very easy to create a network, a user-defined network, instead of a default one. The default one you do not create. It is created automatically by default when the daemon service is created. In case you do not use any network, it will be the one used for any of your containers. So a user-defined network is very easy to create. You simply use the network command, the docker network create command. If different groups of applications have different network requirements, you simply can configure each user-defined bridge separately as you create it. So you can create many or any number of user-defined networks through this command, docker network create, configure them individually, each network, and then on the fly you can attach the ones you want to any of the containers already running in your daemon Docker service. So it's very easy to create user-defined bridge networks, as it's also easy to configure them customly. Each network you configure with specific networking configurations, and then it's also easy to attach any of those networks you want to the containers running the applications of yours. So this is the fourth difference. And the last characteristic or difference between those two subtypes of bridge networks is that, linked containers on the default bridge, they do share environment variables. So this is key for you to understand what we'll be doing in our practices. So in default bridge networks, if you're using the link parameter or the link flag, you have the sharing of environment variables between those containers linked between them. So originally, the only way to share environment variables between two containers was to link them using the link flag. So this is why I started using it as a way to demonstrate how to share variables. You see that we'll be sharing much more variables on the next implementations that we'll be doing in our practices. And we can only share those variables the way we are doing if we use the default bridge network along with the link flag or the link parameter. So if we do not use the link flag, even if we are using the default bridge for both containers, for example, the two containers we've been using so far, we won't be able to share the variables from one container or, for example, from the DB container or DB application to the Spring Boot application in order to use it at the application.properties file at the Spring Boot application. So if we want to share environment variables from one container to another, we gotta use the link flag and the default bridge network. But there are alternatives to that, and that's what we're gonna learn after we exemplify better the implementation of these two subtypes of bridge networks. So explaining better, if you want to set an environment variable for one container, and for example, when you get into that container, you use that variable or in any of the applications running inside it, you do as we've been doing so far. You just use the -e and the name of the environment variable with the equals and the value on the side. So through that, you set the environment variable for that unique container. On the other container also, you can do the same. For that other container, you can set any number of environment variables for that specific container by using the -e parameter. That's what we've been using so far. But in the case you want to share variables between two different containers linked, for example, through the default bridge network, you gotta use the link flag, and that's the more elegant way that we'll be using the examples we've been using so far. We'll be sharing environment variables from one container to another, and not only that, we'll be using the automatic generated environment variables. You see that with the link option, Docker creates automatically many variables, environment variables that not only are created automatically, but they are shared between all the containers linked to that default bridge network and to that specific link between any number of containers. So as the link as well as the default bridge network are actually deprecated or considered legacy in the Docker API, there are other ways, or there are alternatives of not having to use the default network and also not have to use links. You only use links if you're using the default networks. If you do not want to use the default networks and you want to use user-defined networks, you can use those alternatives, and some of them are multiple containers can mount a file or directory containing the shared information using Docker volume. So you gotta use the -v, not only map the volumes from inside the container to an outside path, but you can actually mount a file or a directory containing the shared information or the shared environment variables and get that to inside each of the containers you want. So you can share variables using Docker volumes. The other option, which is the one we will be using at the end of this course, is that multiple containers can be started together using Docker Compose. And if you're using Docker Compose, actually you have an YAML file starting all the containers at once, and inside one same YAML file where you set the running of one or more containers, you can also set the variables that will be shared amongst them. So by default, Docker Compose share the variables of the containers running through the configuration files of the Docker Compose for each set of containers you start. So you don't have to worry about how to share, because Docker Compose, which is another application of Docker, this application automatically and by default manages any environment variables of those containers that it starts. And also you can use Swarm services, which we are not using in this course. You can also use Swarm services instead of standalone containers and take advantage of shared secrets and configs. So these are three alternatives, very used alternatives that can be chosen to not use default networks, and also obviously not link flags. So if you're not using default bridge networks, if you're using user-defined networks, bridge networks, you have to use, if you want to share data between different containers or through environment variables shared between them, you should use any of these three alternatives, which are the best practices advised from Docker. So another and final observation here regarding the differences between these two subtypes of bridge networks is that containers connected to the same user-defined bridge network effectively expose all ports to each other. So remember that we had to use the -p parameter for exposing some ports. For a port to be accessible to containers or non-Docker hosts on different networks, that port must be published using the -p or --publish flag. So what this is saying is that if you are using user-defined bridge network, and if you want one container to access the port, any port of the other container, you do not even have to expose these ports unless you want other containers outside that network or any non-Docker host application, for example a browser, to access that application inside that container. So if you simply want one container to access the other and they are in the same user-defined bridge network, you don't even have to use the -p to expose any ports, because all ports inside one container will be available to the other container or to the other container application to access, and vice versa. But if you want those ports to be accessible to containers on different networks or non-container hosts, for example browsers and applications running on the operating system itself and not on containers or on Docker, you would have to publish those ports the same way that we've been using so far. So in our case, remember that we were not defining any network, so we were by default using the default bridge network on all the running of the containers we've been using so far. So as they were in one same network, both containers, the DBMS container and the springboot container, the ports that one of the applications needed to access on the other container, also as in the user-defined bridge network, they were accessible between the containers but not from outside the container. So for example, you'll see that in our examples for the DBMS container, we did not have to expose the 3306 and 33060 port in order to the Springboot application to access those ports, because both the Springboot application container and the DBMS container, they were both in one same network, which is the default bridge network. So I used on purpose the publishing of the ports, first because we hadn't discussed so far that those two containers were by default linked into one same network, which is the default bridge network. And not only that, but also because we were testing to access those applications from outside Docker. So in the case of the Spring Boot, we were accessing that from a browser, for example, which is installed and running in our operating system, not on Docker, let alone in the same default network. And in the case of the DBMS, also we accessed it from an external client application, in our case the mysql workbench, which also was installed in our OS and not in any container running on the same default bridge network. So just remember that if you want to access any port of a specific container from outside Docker or from any other network not connected to those containers, you gotta expose the ports. But both in the case of the default bridge network as in the case of user-defined networks, if the containers are running attached to the same network, and if you need the ports to be accessed exclusively from one of the containers to another one and not to outside applications, you do not even have to publish those ports. So in the case of our example, one of the refactorings that we'll be doing in our examples, in our running expressions, sentences, is that we'll not have to expose anymore the 3306 and 33060 in the sentence of the running of our MySQL container, because the only application that we'll have in our example to access that container will be in a container running in the same network, either the default bridge network or any user-defined network, bridge network that we want to create and attach to both of them. But in the case we wanted to access any of the ports of any of the applications of any of the containers from outside Docker or from any application in different networks, then we would be obliged to publish those ports with the -p flag. So this last observation is very important, and with that we conclude this part of the documentation in which we saw all the differences and the advantages of user-defined bridge networks compared to the default bridge network, as well as also what the link parameter has to do with the default bridge network, but not to the user-defined bridge network. So in the next topic, we'll be implementing an example of sample containers using both default bridge network with and without the link flag, which is kind of what we was doing so far, and also the same containers attached to user-defined bridge networks that we're going to create. And we'll prove all these differences that we've seen in this topic. The DNS resolution when using user-defined bridges, but not when using the default bridge. The isolation when using user-defined bridge, but not when using the default bridge. The on-the-fly attachment and detachment when using user-defined bridge networks, but not with the default bridge networks. The creation of multiple specific networks and the attachment of multiple networks to each container that we wanna link or we wanna run on those specific networks for specific configurations. We'll not enter in the configurations themselves, but we'll exemplify how those different networks can be created and attached to any container. And very importantly, the sharing of variables when using the default bridge network along with the link parameter, as well as the automatic publishing or implicit publishing of ports for containers running in one same network, but not when running in different networks or when being accessed from outside applications. So that's it for this part, and now let's see. So that's it for this part, and now let's start some practice about it. And in that, I'll also follow here the documentation examples. You can find that also at the guides part of the docs. Here at this part, run your app in production, configuring networks, networking tutorials, and bridge network tutorial. You basically implement these same examples using both the default bridge network as well as user-defined networks and prove all the differences we mentioned in this section. So let's start with our practice and follow these documentation examples.